Welcome to the Curious Voyager. It's lovely to have you here tonight, wherever you happen to be. Maybe you're lying in bed already, with the blankets pulled up, and a single lamp still glowing somewhere across the room. Maybe you're on a couch, or a train, or just sitting somewhere quiet, letting the day finally loosen its grip on you. However you've arrived here, I'm glad you came. Settle in. There's no rush at all.
And before we begin, I'd love to know, where in the world are you watching from tonight? What time is it in your corner of the world? It's one of my favorite things, imagining all the different places people are drifting off from, all the dark windows and quiet rooms scattered across the planet, all of us awake just a little longer, listening to the same gentle story. So if you feel like it, leave a little note. It costs nothing and it means more than you'd think.
And if you enjoy these slow journeys and want more of them, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me genuinely rely on that kind of support more than the big ones ever will. And to those of you who've already subscribed, thank you truly. You're the reason these nights exist at all. Now that's the last bit of housekeeping, I promise. From here on, it's just you and me and a strange little mystery to fall asleep to. Here's the thing about tonight. I'm going to try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something. A fair trade, I think. And you really, truly do not need to follow every word. That's the whole point of a night like this. If you drift off somewhere in the middle, if your eyes get heavy and the words start to blur together into something soft and shapeless, that's not failure. That's exactly what's meant to happen. The story will still be here when you wake. The mystery isn't going anywhere. It's waited 2,300 years already. It can wait for you. So let your shoulders drop. Let the day go. We're going to move slowly tonight. Softly. One small piece at a time. There's nowhere we need to be. Now. Let me tell you about a teenage boy in Tanzania and a freezer, and something that simply should not have happened. His name was Erasto Mpemba, and around the year 1963, when he was still just a schoolboy, sitting in an ordinary classroom on an ordinary afternoon, he stumbled into one of the most quietly stubborn mysteries in all of science. He didn't go looking for it. He wasn't trying to prove anything. He was, of all things, trying to make ice cream. Now picture the scene, because it's a warm one, and warm scenes are good ones to fall asleep inside of. There's a class of students, and they've been making a sweet, milky mixture. The kind of thing you'd freeze to make a simple, homemade ice cream. The usual way to do it, the careful way, the patient way, is to let your hot mixture cool down first. You boil it, you stir it, and then you set it aside and you wait. You let it come down to room temperature, calm and unhurried, before you ever put it in the freezer. That's how it's done. That's how everyone knew it was done. But on this particular day, young Erasto was in a hurry. The freezer was filling up, space was running out, the way it always does when a whole class is trying to use the same small machine at once. And he worried that if he waited the way he was supposed to, there'd be no room left for his mixture at all. So he made a small, slightly impatient decision. The kind of decision a teenager makes without thinking twice about it. He took his mixture while it was still hot, still steaming, still warm to the touch, and he put it straight into the freezer, right next to a classmate's mixture, which had been properly, sensibly cooled down first. And then he waited. Now, here is where you'd expect the story to be utterly boring. You'd expect the cold mixture to win. Of course it should. It had a head start. It was already cool, already part way to freezing, already most of the way there. The hot one had so much further to go. It had to lose all of that heat first, every degree of it, before it could even begin to think about turning to ice. Any reasonable person would bet on the cold one. You'd bet on it. I'd bet on it. It's the most obvious thing in the world. But when Erasto came back and opened that freezer, his hot mixture had frozen first, the warm one, the one with the impossible head start in the wrong direction, the one that should have come in last by a mile. It had beaten the cold one to ice. Let that settle for a moment. Because it really does feel wrong, doesn't it? It feels like being told that if you want to get downstairs faster, you should first run up to the attic. It feels like a small crack in the way the world is supposed to work. And when you notice a crack like that, a little place where reality doesn't quite line up with common sense, it's very hard to look away from it. But here's the part that I find the most human and the most quietly sad, and ultimately the most beautiful. When Erasto told people what he'd seen, when he tried to share this strange little thing he'd noticed, nobody believed him. His teacher didn't believe him. His classmates didn't believe him. In fact, they laughed. The story goes that he was teased, mocked, brushed aside. When he raised the question, his teacher reportedly told him, in so many words, that what he was describing was simply not physics. It wasn't real physics. It was, the implication went, just confusion, a mistake, a silly thing a silly boy thought he saw. There's even a version of the tale where his observation became a kind of running joke. That's Mpemba's physics, they'd say, meaning the kind of nonsense that doesn't actually happen. Imagine that for a moment. Imagine being so sure of something you saw with your own eyes and being told again and again by the people who are supposed to know that you must be wrong, that you didn't really see what you saw, that the world doesn't work that way, so you must be the one who's broken. A lot of people would have let it go. A lot of people would have decided the embarrassment wasn't worth it and quietly folded the strange little memory away and never spoken of it again. It would have been so easy to do. It's what most of us would have done. But Erasto Mpemba didn't let it go, and we'll come back to him. We'll come back to what happened next, and to the one person who finally took the boy's question seriously instead of laughing at it. I promise you that part, because it's the warm payoff of this whole story, and it deserves its own quiet space later on. But for now, just hold on to him. Hold on to that image of a teenager, sure of something true, standing alone against a room full of people, telling him he was wrong. Because the strangest thing of all, Dasha, the thing that turns this from a charming little anecdote into a genuine mystery worth a whole night of your time, is this. He was right. And more than half a century later, with all of our laboratories and all of our instruments and all of our brilliant minds, we still cannot fully agree on why. So let me tell you gently and carefully exactly what it is we're dealing with. Let me give it its proper name and its proper shape before we go any further into the dark. What that schoolboy noticed is now called the Mpemba effect, named fittingly after the very boy who was laughed at for it. There's a kind of justice in that, isn't there? That the thing nobody believed now carries his name in textbooks and journals and competitions around the world. The teasing didn't last. The name did. And the Mpemba effect, put as simply as I can put it, is this. Under certain conditions, a hotter body of water can freeze faster than a colder one. Now, I want you to notice the most important little phrase in that sentence, because everything tonight hangs on it. The phrase is under certain conditions, not always, not reliably, not every time you try it in your own kitchen, under certain conditions. This is the honest heart of the whole thing, and I want to give it to you straight, right at the start, so you're never misled. The Mpemba effect is real in the sense that it has genuinely, repeatedly been observed. Careful people doing careful experiments have watched hot water beat cold water to ice more than once, in more than one place. It happened. It happens. But it is not universal. It does not happen every single time. It is, in fact, notoriously, almost maddeningly difficult to reproduce on demand. You can set up an experiment, do everything you think you're supposed to do, and watch the cold water win exactly the way common sense says it should. And then you can change something tiny, the container, the amount, the starting temperature, the way the freezer is running that day, and suddenly the hot one wins.
And nobody can tell you with full confidence ahead of time which way it's going to go. So it's slippery. It's a phenomenon that seems to come and go, that appears for some people and hides from others, that shows up in one lab and refuses to show up in the lab next door. And that slipperiness, that refusal to behave the same way twice, isn't a flaw in the story. It's one of the central facts of it. It's a huge part of why this mystery has stayed a mystery for so long.
You can't easily solve a puzzle that won't even sit still long enough to be properly looked at. But let's go back, way back, to the feeling you had a moment ago, that little crack in common sense, because I want us to really sit inside it for a while, slowly, the way you'd sit inside a quiet room and let your eyes adjust to the dark. I want us to understand exactly why this feels so wrong, so that later when we look at the possible explanations, you'll feel the full weight of how strange they have to be to account for it. So, here is the settled world, here is the way things are supposed to be, the comfortable, obvious picture that almost everyone carries around without ever questioning it. Cold things are closer to freezing than hot things, that's just true. It's about as basic a fact as we have. If you want something to freeze, you cool it down, and the colder it already is, the less cooling it has left to do. A glass of cold water is most of the way to ice already. A glass of hot water is a long, long way from it. There's a whole journey of heat that the hot water has to shed, has to lose degree by degree by degree, before it can even arrive at the same starting line the cold water is already standing on. Think of it like two travelers heading to the same far-off town freezing, let's call it. The cold water starts the journey just a few miles out. It's nearly there. You can practically see the lights of the town from where it stands. The hot water, meanwhile, starts way back at the far edge of the map, with a vast distance to cross before it even reaches the spot where the cold water began. Common sense says the one that's nearly there should arrive first, obviously, every time. How could it possibly be otherwise? How could the traveler who starts further away, who has more ground to cover, who has every disadvantage, how could that one ever arrive first? And yet, that's the whole mystery, wrapped in a single image. Somehow, under the right conditions, the traveler who started further back arrives first. The hot water, with all that extra distance to travel, with that enormous handicap, still gets to town freezing before the cold water that was practically standing at the gates. It shouldn't happen. By every gut instinct we have, by the simplest, most obvious reasoning, it cannot happen. And it does. Now when something like that happens, when the world quietly contradicts something we were absolutely sure of, there are really only two honest responses. One is to do what that classroom did and laugh and decide the person must be mistaken, because surely the world makes more sense than that. And the other, the better one, the one that lies at the very heart of every good mystery and every bit of real science, is to lean in closer and say, wait, show me. Let me look again. What if I'm the one who's been wrong all along? That second response is so much harder than it sounds. It means being willing to let go of something comfortable. It means admitting that the obvious thing, the thing everybody knows, might just not be true. And most people, most of the time, won't do it. It's so much easier to laugh. But hold this thought, because it's going to grow into something much larger as our night goes on. The reason this little kitchen mystery matters, the reason it's worth more than just a clever party fact, is that it's a tiny, perfect example of something deeper. It's a reminder that the world is still, even now, full of simple things we don't understand, things sitting right in front of us, things you could test yourself tonight with nothing but 2 cups and a freezer. And yet beneath that simple surface, a question that has genuinely defeated some of the smartest people who ever lived. Because here is the part that I find almost dizzying in the most pleasant, drifting sort of way. That schoolboy in 1963? He wasn't the first to notice this. Not by a long, long way. He wasn't the first by years or by decades or even by centuries. He was, give or take, the first in about 2,300 years. I'll say that again, slowly, because it's the kind of number that's almost too big to feel the first time it goes past you. 2,300 years, roughly 23 centuries. That's how long ago the very first written record of this strange effect appears, long before freezers, long before refrigerators, long before electricity, long before the modern idea of an experiment, long before almost anything you'd recognize as science at all. Someone all that time ago sat down and wrote that water which had first been heated seems to freeze more quickly. And this is the astonishing part, it was noticed and written down and noticed again and written down again by some of the greatest thinkers in all of human history. And still, after all of that, after 23 centuries of clever people scratching their heads at it, we do not have a single agreed-upon explanation for why it happens. 23 centuries. Empires rose and fell in that gap. Whole languages were born and died. Humanity learned to split the atom, to map the genome, to send machines beyond the edge of the solar system, to peer back almost to the beginning of time itself. We figured out so much. We unlocked secret after secret after secret of how the universe is put together. And this small, humble, kitchen table thing, this question of whether warm water can beat cold water to ice and why, this one slipped through our fingers the entire way. It's still slipping through them now, tonight, as you lie there listening.
Isn't that something? Isn't that a strangely comforting thought to carry towards sleep? That for all our cleverness, for all our marvels, the universe still keeps a few little secrets tucked away in the most ordinary places. That there's still mystery in a glass of water. That not everything has been solved and maybe not everything needs to be.
So that's our journey for tonight, laid out gently before us like a path you can see winding off into soft hills. We're going to follow this question slowly all the way down. We're going to go back to where it first appears 2,300 years ago and meet the ancient mind who first wrote it down. We're going to trace the long, strange silence that followed. The centuries where it was noticed and then forgotten. Noticed and then forgotten, like a tune nobody could quite remember the rest of. We're going to return to our schoolboy, Erasto, and finally meet the one person who chose to believe him, the physicist who took a ridiculed teenager's question seriously and changed everything. And then once we've earned it, we're going to lay out the suspects, because there are suspects, several of them, possible explanations for how on earth this could happen. There's something to do with the water quietly turning to vapor and floating away. There's something to do with the way warm water stirs and churns and moves within itself. There's something genuinely odd about water that can sink below the freezing point without actually freezing. There's something about the invisible gases dissolved inside a glass of water, the ones you never think about. We'll meet each of these possible answers in turn, slowly, gently, and we'll see what makes each one tempting. And we'll see, just as honestly, exactly why none of them has ever quite managed to win. Because that's the honest truth I want to keep faith with you on all night long. I'm not going to give you a tidy answer at the end. I can't. Nobody can. There are videos and articles all over the world that will recite a list of explanations and then announce briskly that one of them is the solution and send you on your way feeling satisfied. But that wouldn't be true, and I'd rather give you something true than something tidy. The honest, more interesting reality is that none of these explanations has won. The case is still open, and there's even, and we'll get to this much later, when you may well already be asleep, there's even a serious argument made by serious scientists not so long ago that the whole effect might not be a real solid thing at all, that it might in a sense be a kind of mirage, an artifact of how we measure things, a ghost we've been chasing through the cold. But that's for later. That's a twist for the deep part of the night when the room is darkest and the story has settled into its bones. For now, all you need to hold are a few gentle shapes in the dark. A boy, sure of something true, laughed at by everyone around him. A crack in common sense, the traveller who started furthest away, somehow arriving first. And a span of 23 centuries across which the cleverest people who ever lived noticed this little impossibility and wrote it down and shrugged and could never quite explain it. That's a lot of mystery for a glass of water, and we have all the time in the world to wander through it. So let's go back now. Back past Erasto and his freezer, back past every refrigerator that ever hummed in a kitchen, back before electricity, back before so much of what we take for granted, back to the ancient world where someone first looked at a pot of water that had been warmed and noticed something that didn't make sense and, instead of laughing, did the rarest and bravest thing a mind can do. He wrote it down anyway. Let's go and meet him. His name was Aristotle, and you may have met him before in some other corner of your education, as a serious man in marble, the kind of figure carved into the front of libraries. But set that statue aside tonight. Picture instead a man simply curious about the world, walking through the warm Mediterranean air more than 2,300 years ago, paying attention to ordinary things the way a child does before the world teaches us to stop noticing. Around the 4th century before the Common Era, Aristotle wrote a work called the Meteorologica, which sounds like it should be about weather, and in a way it is, though it wandered into all sorts of questions about the sky and the air and water and how the world behaves, and tucked inside it, almost in passing, is a small observation that should stop you in your tracks, if you let it. He wrote that water that has been heated beforehand freezes more quickly than water that has not. Let that settle for a moment. 2,300 years ago. No freezers, no thermometers as we'd know them, no clocks ticking off precise seconds. And yet here is a man writing down the very same strange thing that a Tanzanian schoolboy would notice with his ice cream mix more than 2 millennia later. The same little impossibility observed across an almost unimaginable gulf of time by two people who could never have met, who spoke different languages, who lived in worlds that would have been mutually unrecognizable. And Aristotle didn't just notice it. He gave a little detail, the kind of detail that tells you a real person actually watched this happen. He mentioned that people who wanted to cool water quickly would first stand it out in the sun, would warm it, in other words, on purpose, because they had learned somehow through ordinary kitchen and courtyard experience that this was the faster road to cold.
Isn't that lovely, a piece of folk wisdom passed hand to hand, that the warm path is sometimes the quicker way down? People knew this, they used it, they just couldn't say why.
Now, Aristotle did try to explain it because that was his nature. When he was a man who wanted reasons for things, he reached for an idea he called anti-peristasis. Don't worry about the word. You will not need it in the morning, and there's no need to hold on to it now. It's just an old Greek name for an old Greek hunch. The rough idea was that a quality could be intensified by being surrounded by its opposite. that cold, hemmed in by heat, would somehow gather itself and grow stronger, the way you might imagine something concentrating when it's pressed in from all sides. It's a beautiful, intuitive sort of guess. And it's almost certainly wrong. We'll let it go gently, the way you let go of a thought as you drift off. Not because it was foolish, but because it had done its work simply by being written down. Because here is the thing about Aristotle's little note. It survived, it got copied and recopied, carried through centuries of candlelight and quiet libraries, and it kept the observation alive, faint, flickering, but never quite extinguished. The fact didn't have an explanation, but it had a witness. And sometimes that's enough to keep a mystery breathing, and then for a very long time, almost nothing happened. This is the strange, slow middle of our story, a part where the trail goes quiet. Centuries pass, empires rise and fade. The observation sits there in old texts like a coin dropped between the floorboards, occasionally glimpsed, mostly forgotten. Nobody solves it because nobody is really trying. It's a curiosity, a footnote, the kind of thing a scholar might mention and then move past, the way you might notice an odd cloud and then look back down at your road. But it never disappears completely. And every so often, across that long quiet, a remarkable mind stumbles onto the very same thing and writes it down all over again, almost as if rediscovering it for the first time. Fast forward then, past the fall of the ancient world, past the long medieval centuries, all the way to the early 1600s, to the dawn of what we'd now call modern science. A new way of thinking was taking hold. The radical notion that you shouldn't just reason about the world from your armchair, but should go and look and test and observe. One of the loudest champions of this new way was an Englishman named Francis Bacon. Bacon was, among many other things, a philosopher of method, a man obsessed with how we ought to gather knowledge properly rather than just inheriting old opinions. And in 1620, in a famous work called the Novum Organum, which means roughly the new instrument, his new tool for thinking, he set down, among countless other observations about nature, this small remark: that water slightly warmed freezes more readily than water that is quite cold. There it is again, the same impossibility, different century, different country, different language, a man who almost certainly hadn't read that particular line of Aristotle's with this in mind. And yet here he is, independently noticing the warm water beating the cold to the finish. It's almost eerie, isn't it, when you lay them side by side, as though the world keeps leaving the same little clue out in plain sight, century after century, waiting patiently for someone to finally pick it up and understand it. And Bacon, for all his brilliance, for all his insistence on testing and looking, didn't crack it either. He noted it. He moved on. The coin stayed under the floorboards. But he wasn't the last great mind to trip over it. Because around the same era, across the Channel in France, another towering figure was wrestling with the nature of the world. A man whose name you've almost certainly heard, even if everything else about him has faded. René Descartes. Descartes is the one usually remembered for that famous line about thinking and existing, the philosopher who tried to tear down everything he thought he knew and rebuild it from the ground up on certainties. But he was also deeply curious about the physical world, it's about light and weather and the behavior of ordinary matter. And in his writings from that period, he too made note of the phenomenon that water which has been kept hot freezes faster. 3 names now: Aristotle, Bacon, Descartes. 3 of the most influential thinkers in the entire history of human thought, separated by thousands of years and thousands of miles, and every one of them stopped at some point and noticed this same gentle absurdity. The warm thing reaching the cold finish line first. And not one of them could explain it. I want you to sit with the strangeness of that for a moment here in the quiet. We tend to imagine that the great questions science hasn't answered must be the enormous ones. The edge of the universe, the inside of a black hole, the spark of consciousness itself, the faraway things, the things you'd need $1 billion machine even to glimpse. But this isn't that. This is a glass of water in a freezer. This is something so small, so domestic, so utterly within reach that a teenager could discover it with leftover ice cream mix, and Aristotle could spot it without so much as a thermometer. And yet it slipped through the fingers of the sharpest minds of the ancient world, of the Renaissance, of the scientific revolution, right there, held in the palm, and still it would not give up its secret. That's the quiet wonder I'd like you to carry as you drift, if you're still with me at all. And it's perfectly fine if you're not, if your eyes have already closed, and these words are just a warm murmur in a dim room. The ideas will keep. The water will still be there in the morning, behaving exactly as strangely as ever. So here is the shape of where we've come, gently traced. An observation as old as written philosophy. A trail that goes quiet for centuries, then flares up again whenever a curious enough mind happens to look. A coin dropped between the floorboards of history, glinting now and then, picked up, turned over, set back down, unexplained. And then, at last, someone who wouldn't set it back down. Because for all of Aristotle's careful watching, for all of Bacon's new instruments, and Descartes' relentless doubt, the observation remained exactly that. An observation, a noted oddity. That's funny, scribbled in the margins of much grander projects. Nobody had taken it by the collar and demanded an answer. Nobody had built it into a real, sustained scientific question, the kind with a name and a paper and a community of people arguing over it late into the night. That part of the story, the part where this sleepy little kitchen curiosity finally becomes a genuine scientific problem, with experiments and arguments and rival explanations all jostling for the truth, that part doesn't begin in ancient Greece or in a grand European court or in any of the places you might expect. It begins, of all places, in a school kitchen in Tanzania, with a freezer that was filling up fast, with a row of boys all trying to claim the same cold shelf for their ice cream mix, and with one stubborn teenager who was about to do the thing that none of those famous men, for all their genius, had quite managed. He was going to refuse to let it go. His name was Erasto Mpemba, and in 1963 he was a student at Magamba Secondary School in Tanzania, doing what schoolboys do, trying to get his ice cream mix into the freezer before everyone else claimed all the space. The class had a project. They were making ice cream, which meant each student was working with a mixture of milk, sugar, cream, and whatever went into the school's particular recipe, and each student needed a slot in the communal freezer. The freezer was small, the class was not, and if you waited too long to put your mixture in, if you let it cool down completely to room temperature first, which was the sensible, careful, patient thing to do, you might find all the shelves already taken and your ice cream unfinished, and you with a problem. So Erasto Mpemba did not wait. He put his mixture in while it was still hot. Now, in one version of the story that is very easy to tell, this is simply a boy being impatient, cutting corners, doing the thing you're not supposed to do. In another version, this is the version that turns out to be the more interesting one, this is a boy doing exactly what a good scientist does, even if he doesn't know it yet. He is running an experiment, not a careful, controlled, written-down experiment with a hypothesis and a method and a clean set of results. Just the instinctive, improvised, slightly desperate experiment of someone who wants to solve a practical problem and doesn't have the luxury of following all the proper steps. He noticed something. The hot mixture froze first, not the one that had been sitting patiently at room temperature, cooling slowly, doing everything by the book. His The hot one. The one that should have needed to come all the way down from a high temperature before it could even begin the journey to ice. His froze first. He asked his teacher about it. The teacher told him he was wrong, that what he thought he had observed was simply impossible. Cold freezes faster than hot. This is not a mystery, this is not a question, this is how the world works. And if your hot mixture seemed to freeze first, then you made an error somewhere, or you remembered it wrong, or you are, in the polite language of classrooms, confused. His classmates agreed with the teacher, which is usually how these things go. Here is one of the things that makes this story so quietly remarkable. Mpemba didn't accept that, not because he was stubborn in a difficult way, or because he was the sort of student who argues with teachers for the pleasure of it, but because he had seen what he had seen. He had stood in that kitchen and he had watched, and something had happened that didn't match what he was being told should happen. And whatever else was true, that gap between what he'd observed and what authorities said was possible, refused to close in his mind the way it was supposed to. So he kept asking. He asked his physics teacher. He asked other teachers. He got more or less the same answer each time, delivered with varying degrees of patience. Hot water does not freeze faster than cold water. This is basic physics. Please move on. And then, a few years later, a man named Dennis G. Osborne visited the school. Osborne was a physicist at the University College in Dar es Salaam, and he had come to give a talk, the kind of visiting academic event that schools arrange partly for the students, and partly because it sounds impressive on the prospectus. He spoke, answered questions, and at some point during the session, or perhaps just after, Erasto Mpemba asked him the question. He asked it directly: why does hot water freeze faster than cold water? The room, by most accounts, did something close to laughing. The implication was clear enough. This was not a real question. This was a mistake, or a confusion, or a gap in basic understanding wearing the costume of a question. The kind of thing you ask before you properly know how the world works, and then stop asking once someone explains it. But Osborne didn't laugh. He paused, and instead of explaining to the teenager why the observation was impossible, he said something more honest. He said, essentially, "I'm not sure, let me look into it." What Osborne did next is one of the most important small choices in this entire story. He went back to his lab and he ran experiments, not because he was certain Mpemba was right, he probably wasn't certain of that at all, but because the question deserved to be tested, which is not the same thing as deserving to be believed. You don't have to believe an observation to take it seriously. You just have to be willing to be surprised. And he was. The experiments confirmed it. Under certain conditions, the hot water was reaching its frozen state before the cold. Not always, not in a way that could be predicted with perfect reliability, but often enough and consistently enough that the effect was real, or at least real enough to be worth writing about. And so in 1969, Erasto Mpemba and Dennis G. Osborne published a paper together in the journal Physics Education. The paper was called, with what you have to admire as a very dry sense of scientific humor, simply, "Cool?" That paper is where the modern story of the Mpemba effect begins. That is the document that anchored the observation to a name, gave it a place in the literature, and started the long, tangled, still unfinished argument about why it happens and whether it can be trusted. Because of that paper and the open-minded physicist who took a schoolboy's question seriously, an observation that had been bobbing around the margins of human thought for over 2,000 years finally had a proper scientific home. He was right. The boy who was laughed at was right, at least in the sense that mattered. There was something genuinely worth looking at. Something that didn't fit neatly, that resisted the obvious explanation, that remained standing after a physicist took careful aim at it. That is a good thing to know. And if you are still listening, still drifting somewhere in the soft hours of the night, let that settle for a moment before we go further. A boy noticed something. He was told he was wrong. He kept asking. A physicist listened. And now this observation, this kitchen curiosity, this small, strange fact about freezers and ice cream and stubborn adolescent attention carries his name through the scientific literature. Erasto Mpemba, the Mpemba effect. But here's what makes all of that even stranger. It wasn't new, not even close. Because while 1963 feels like the beginning, while the school kitchen in Tanzania and the young student with his ice cream mix and the visiting physicist have all the shape of an origin story, the truth is that this particular observation had already been made many times by very serious people in very different places across a stretch of time so long that framing it properly requires a moment of genuine stillness. We have to go back, way back. All the way back, in fact, to the 4th century before the Common Era, to a world without freezers, without ice cream machines, without any of the refrigeration technology we take entirely for granted. A world in which people still needed cold, still wanted cold, and had to manage the getting of it through far more patient and labor-intensive means. Aristotle was born in 384 BCE in Stagira in what is now northern Greece, and he spent his life doing something that very few people in the ancient world, or in any world, manage with such systematic dedication. He watched, he categorized, he wrote everything down. He looked at the natural world as a set of phenomena waiting to be understood, and he spent decades asking the same kinds of questions that a physicist or a biologist or a naturalist would ask today, working with the tools available to him, which were mainly careful observation and careful reasoning. In his Meteorologica, a work on weather, climate, water, and the broader behavior of the natural world, Aristotle wrote something that, if you read it now, knowing what you know, produces a very specific kind of quiet astonishment. He wrote that water that has previously been heated is more readily frozen. He was more specific than that, actually. He described the practice, apparently common enough to be worth noting, of people who wished to cool their water quickly, first standing it in the sun to heat it up. Because warmed water, in his observation, would then cool and freeze faster than water that had not been warmed. He offered an explanation for this, as he always did. He called it antiperistasis. The word is long and Greek and sounds more scientific than it probably was. It referred to a kind of oppositional intensification, the idea that a quality becomes stronger when it encounters its opposite. That heat, meeting the surrounding cold, would react against it with greater force, driving the temperature down faster. A bit like the way a current of air seems to push harder when it hits a wall. It was, by modern standards, not a very good explanation, but it was an explanation, which is not nothing, and the observation beneath it, that was real. That was careful watching translated into careful writing. Aristotle sat in the ancient Mediterranean and looked at water, and he noticed something that would not be formally confirmed for another 2,300 years. Just let the scale of that number rest somewhere in the back of your mind for a moment. 2,300 years, roughly 100 generations. Every grandmother and great-grandmother and great-great-grandmother and all the great-grandmothers behind them, stretching back so far that the thread disappears into a time when the things we call history were still being lived as ordinary life. Aristotle noted this thing, and the world moved on, and centuries passed, and nothing was done about it. And here we still are, not fully understanding it. The observation went more or less quiet after Aristotle. That is not quite the same as being ignored. It lived in his texts, which were copied and studied and argued over across the following centuries in ways that profoundly shaped the course of Western intellectual history. Anyone who read the Meteorologica carefully enough would have encountered it. But it was one observation among thousands, and nobody, in the long centuries that followed, seems to have picked it up and run with it in a sustained way. Until Francis Bacon. Bacon was born in 1561 in London, and he is one of the central figures in the story of how modern science came to exist. He spent much of his intellectual life arguing, with considerable force and eloquence, that the right way to understand the natural world was not to reason about it from first principles and ancient authority, but to actually look at it, to gather evidence, to run experiments, to build knowledge from observation upward rather than from grand theories downward. This sounds so obvious from where we sit now that it barely seems worth saying. In 1600, it was a genuinely radical position. His great work, Novum Organum, the new instrument published in 1620, is full of careful observations and examples and attempts to lay out a proper method for investigating the natural world. And somewhere in that book, tucked in among all the methodology and argument, Bacon notes that water which has been slightly warmed freezes more readily than water that is quite cold more readily. The same observation, different country, different century, different man, different context, but the same stubborn, inconvenient fact surfacing again. Bacon was interested in it as an example, a data point in his broader argument about the importance of collecting observations rather than trusting received wisdom. He wasn't setting out to explain it. He was using it as evidence that the world is full of things that don't behave the way we assume, and that the only honest response to that is to look more carefully. And then, in approximately the same period of European intellectual history, René Descartes encountered it too. Descartes is most famous for a sentence about thinking and existing, but he spent a great deal of his life thinking about natural philosophy as well, about the physical world, about matter and motion, about how things actually work beneath the surface of appearances. He recorded the observation that water which has been kept hot freezes faster. This is in his writings from the era of his Discours de la Méthode and the associated treatise Les Météores, where he thought about weather and the behavior of water with the same precise, skeptical attention he brought to everything. Three great minds, then. Across a span of roughly 2,000 years, Aristotle in the 4th century BCE, Bacon in 1620, Descartes in the same generation as Bacon, each noticing the same thing, each writing it down, each moving on without fully resolving it. There is something almost tender about this if you let yourself feel it. These were not small thinkers, these were not careless people. Aristotle essentially invented systematic natural inquiry. Bacon argued the world into the scientific method. Descartes rebuilt philosophy from the ground up. And this one little observation, to water heated, then cooled, in a kitchen or a courtyard, or wherever it was that they happened to be watching, this one kept arriving on their doorstep, was noted, was recorded, and then was quietly set aside because they had bigger mountains to climb, and this one particular foothill would simply have to wait. So it waited. For centuries, the observation existed largely in the margins, not forgotten entirely. It was there in the texts, there for anyone who read carefully enough, but not really alive either, not being actively argued over, not being tested in a sustained way, not carrying the kind of scientific momentum that eventually turns an observation into a theory and a theory into an understanding. This is one of the quieter mysteries inside the bigger mystery. Why didn't anyone in all those intervening centuries pick it up and push harder? There were brilliant people thinking about heat and cold and the behavior of water throughout the 17th century and the 18th and the 19th. The physics of heat transfer became a serious scientific discipline. Thermodynamics was built with tremendous care and mathematical sophistication in the 1800s. And yet this particular puzzle, warm water, cold water, which freezes first, just sat there. Part of the answer is probably that the effect is unreliable. It doesn't always happen. You can go to your kitchen right now and do the experiment and quite possibly observe nothing unusual at all which would confirm your existing belief that cold water freezes first and leave you with no puzzle to explain. The intermittency of the effect is part of what made it so easy to treat as an outlier, a fluke, something that could be set aside in favor of the very clean and mathematically tidy principle that hotter things cool more slowly. Newton's law of cooling, which emerged from the late 17th century, gives a precise mathematical description of how a warm object loses heat to a cooler environment. According to that framework, a hotter body of water should take longer to cool to freezing than a cooler one. This is correct in general. This is good physics, and good physics, when it is very clear and very well established, has a tendency to make anomalous observations seem less urgent. If the theory is sound and the observation doesn't quite fit, it is easy to assume the observation was imprecise rather than the theory incomplete. So the observation slept. It slept through the grand age of thermodynamics. It slept through the Industrial Revolution and its enormous interest in heat and engines and the management of temperature. It slept while physicists built quantum mechanics and general relativity and the Standard Model, solving some of the deepest mysteries in the universe, while this particular small, domestic, stubborn puzzle sat quietly in an icebox somewhere, waiting. And it was still sleeping, still waiting, when a boy in Tanzania stood in a school kitchen with a container of hot ice cream mix and not enough room in the freezer, and made exactly the same observation that Aristotle had made, alone, with no knowledge of Aristotle, and refused to accept the explanation that he must simply be wrong. There is something beautiful about that. About the way the same true thing keeps arriving, uninvited, in the minds of people who are just paying attention. About how 2.5 millennia of human history and scientific development could pass, and this small, specific, counterintuitive fact could remain exactly as puzzling, exactly as observed, and exactly as unexplained as it was when someone first stood a clay jar of water in the Mediterranean sun to make it cool faster. Some puzzles are patient. This one is very patient. Now, we have arrived gently and by the long route at the point where the observation finally has a name and a paper and a proper place in the literature. 1969, Mpemba and Osborne. Cool? Physics education. The question is official. The effect is real enough to write about. And the scientists of the world can begin the work of arguing about it properly. But before we get to the arguments, and there are very good arguments, strange and counterintuitive and surprising arguments, all of which we will walk through slowly, it is worth spending just another moment with Dennis Osborne. Because what he did matters in a way that goes slightly beyond the physics. When Mpemba asked his question in front of a room that was largely laughing at him, Osborne could have done what everyone else had done. He could have delivered the correct textbook answer. Hot things cool slowly, cold things freeze first. This is Newtonian thermodynamics. This is how the world works. Thank you for your question and please sit down. He was a physicist. He had the authority to close the question, and closing it would have been the comfortable thing to do. Instead, he held it open. He did not say, "You're right." He didn't know that yet. What he said, in effect, was, "That's an interesting claim, and claims like that deserve to be tested, not assumed away." And then he went and tested it. That is, in miniature, what the scientific method is supposed to look like. Not the grand sweeping narrative of genius and revolution, but the ordinary, quiet insistence on actually checking, on not assuming that your existing theory explains an anomaly until you've genuinely looked at the anomaly, on being the kind of person who, when a teenager in a school in Tanzania tells you something seems wrong, finds out whether it actually is.
Osborne found that it was not wrong, not at any rate in the simple way. The effect was there, elusive, inconsistent, maddening in its refusal to behave the same way every time, but there. Real enough to publish, real enough to name.
And from 1969 onward, the question that Aristotle had noted in passing, that Bacon had catalogued, that Descartes had recorded, that a schoolboy had refused to let go. The question had a proper name and a proper home and a proper, ongoing, thoroughly unresolved scientific argument attached to it, the Mpemba effect. It is worth saying what that name means in the full sense. It doesn't just mean the observation, it doesn't just mean the phenomenon. It is also a record of a particular kind of courage, the quiet courage of someone who saw something clearly and kept saying so even when the room was laughing. And it is a record of a particular kind of scientific virtue, the willingness of a more powerful person to take a less powerful person's observation seriously, to test it rather than dismiss it, to let the world be strange if the world insists on being strange. These things matter. They matter scientifically because good science depends on exactly this kind of attention and humility, and they matter humanly because every so often it is worth remembering that the history of ideas is not only the history of famous men in great institutions making planned discoveries. It is also sometimes the history of a boy in a school kitchen watching something happen in a freezer and not being willing to pretend he didn't see it. So here is where we stand in the long drifting arc of tonight. An observation noted by Aristotle around 350 BCE, a roughly 2300-year gap during which Francis Bacon and René Descartes each independently recorded the same thing, and the scientific world largely moved on. A teenager in Tanzania in 1963 mocked for his observation, a physicist who listened, a paper published in 1969, and a mystery, still open, still turning slowly in the light, not yet resolved, that now officially carries the name of the boy who refused to let it go. That is the history. And it brings us naturally to the question that the history has been building toward all this time. The question that Aristotle couldn't answer, that Bacon didn't pursue, that Descartes left aside, that Mpemba asked so persistently and Osborne set out to investigate, and that generations of physicists and chemists and curious people have been arguing about ever since. Why? Why would hot water freeze faster than cold? What possible mechanism what chain of physical events could allow something that starts further from its destination to arrive there first? Because here is the thing about this puzzle that makes it genuinely interesting rather than merely counterintuitive. It isn't just surprising. It's surprising in a way that seems to violate something very fundamental. The journey from hot to frozen is longer, by definition, than the journey from cold to frozen. If you start at 80 degrees Celsius and you are heading for 0, you have a farther road to travel than if you start at 20 degrees. Every thermometer says so. Every piece of physics we have built says that a hotter body of water must pass through all the temperatures a colder body passes through, and then some extra ones besides. How can the longer journey be the faster one? There are answers to this. Several of them, in fact, and none of them are quite complete, and none of them have won, and some of them contradict each other. And one very serious scientific paper published in 2016 argues that the whole effect may not be reliably real enough to explain at all. But those are the answers, and each one deserves to be met slowly and properly, turned over in the mind like a smooth stone, examined for what it gets right, and what it leaves still unexplained. And if you are comfortable where you are, if your blanket is settled and your eyes are somewhere between open and closed, and the night is doing what nights do, then there is no rush. We will walk through each of them in turn. Not to arrive at a clean conclusion, because the clean conclusion has not been written yet, and pretending otherwise would be the kind of thing that sounds satisfying in the moment, and leaves you feeling gently cheated when you think about it later. Instead, we will walk through each explanation the way you walk through a house of rooms, opening each door, looking carefully at what's inside, and then moving on to the next one. Some rooms are larger than others, some are more convincing, One or two of them might be locked, or might not lead anywhere at all. But the walking is the point. The slow, curious, unhurried walking in the quiet of whatever hour this is for you. So let's begin, shall we? The first explanation anyone tends to reach for, the most intuitive, the one that arrives almost before you've finished asking the question, is evaporation. Think about a hot cup of tea sitting on a table. You can see it, if the light is right, releasing a thin curl of steam into the air above it. That steam is water, actual molecules of water detaching from the surface of the liquid and floating upward into the room. When water evaporates, it loses mass, and it loses heat along with it. Evaporation is a cooling process, which is why sweating cools you down, and why the air near a lake feels different from the air in a car park, and why a wet cloth on a forehead does what it does. So if you start with a container of hot water, it will evaporate more quickly than a container of cold water. By the time it has cooled down to the starting temperature of the cold water, it will have lost some of its mass, some of its actual water, to the air. It will, in other words, be a slightly smaller quantity of liquid. And a smaller quantity of liquid has less to freeze, less work for the cold to do, a smaller problem to solve. This is a genuinely reasonable idea. It has a clear mechanism. It follows from well-understood physics, and you can observe the steam yourself, which always makes an explanation feel more trustworthy. Aristotle might have been nodding at something like this, in his way, and without the vocabulary for it. But there is a but, and it is a fairly significant one. Scientists have run experiments in sealed containers, not open bowls or cups sitting on a shelf, but closed systems where no water can escape, no steam can drift away into the room, no evaporation is possible. The hot and cold water are sealed in equal amounts, going nowhere. And in some of those experiments, the Mpemba effect still appears. The hot water still freezes first, or seems to, even when evaporation has been completely removed from the equation. Which means that evaporation might contribute. It might be part of what's happening, one thread in a tangle, but it cannot be the whole story, because the story continues even when that thread is cut. This is a recurring frustration in the literature on the Mpemba effect, and it's worth holding gently as we go. For almost every proposed explanation, there exists a set of experimental conditions designed specifically to isolate that factor, to test whether it is the cause or merely a companion. And for almost every proposed explanation, the results come back muddled. The effect appears sometimes with the factor, and sometimes without it. The factor seems to help, but its absence doesn't reliably eliminate the phenomenon. It is as if the mystery is made of several overlapping causes, none of which is sufficient on its own, and different combinations of which are active in different experiments, which is exactly the kind of thing that makes a scientific question very hard to settle. But we are getting ahead of ourselves. Evaporation was the first door, and we've opened it and looked inside and seen that it is real but incomplete. The next one is a little more interesting, more hidden, less visible to the eye. It involves the way hot water moves. When you heat a liquid, not boiling it, just warming it significantly, you create temperature differences within it. The very bottom of the container, closest to the heat source, gets warmer first. The top and the sides may still be cooler. And in a liquid, temperature differences create movement. The warmer, less dense water rises. The cooler, denser water sinks. This circular churning motion is called convection, and you can sometimes see it in a very hot, clear liquid. The faint shimmer of movement, the slight distortion, the liquid in gentle, invisible circulation. Now put that moving, convecting liquid into a freezer. The convection doesn't stop immediately, the hot water continues to move. And that movement means that the warm water from the interior of the liquid is constantly being brought up to the surface, where it is exposed to the cold freezer air and can shed its heat more quickly. The cold water near the top, meanwhile, sinks to the bottom, circulating the coolness through the whole volume. This ongoing movement, this internal churning, may mean that the hot water is losing heat to the freezer more efficiently than the cold water, which sits more still. The hot water has convection working for it, creating a kind of internal pump that moves warmth to the surface and away. The cold water is quieter, more settled, and perhaps less efficient at this surface-level heat loss. There is also a subtler version of this. Hot water cooling in a freezer tends to develop what researchers sometimes call a hot top. As the outer edges cool and the middle stays warm, the surface of the liquid may actually be warmer than the bottom, a kind of temperature inversion. And because the surface is in direct contact with the cold freezer air, a warmer surface loses heat faster. It radiates more, it conducts more. The very strangeness of the temperature distribution that hot water creates might actually accelerate its cooling. Convection is, in many ways, a more sophisticated explanation than evaporation. It involves the behavior of the water as a dynamic, living system, rather than just a static container of liquid slowly losing mass. It's the kind of explanation that reveals that water is not simply sitting there waiting to be cold. It's doing things, moving, circulating, distributing its own warmth in ways that are constantly shifting. And yet convection also cannot be the complete answer. Experiments have been done in conditions where convection is deliberately suppressed, using very thin containers, or very small volumes, or specific temperature profiles that don't favor it. And the Mpemba effect has been observed in some of those conditions anyway. Convection seems to be a real contributor, in many cases perhaps a very important one. But it leaves something unexplained at the edges. You can feel the shape of this problem emerging slowly in the comfortable dark. Every door we open leads into a real room with real furniture, but none of the rooms quite contains the whole answer. We are not walking through a house toward a final room with everything inside it. We are walking through a house where the architect left the plans unfinished. That is not a failure, actually. It is the most honest thing we can say. There is a third explanation, and this one is perhaps the most elegant, the most surprising, the one that, when you understand it, produces the quiet satisfaction of a well-told story, even though it too comes with the caveat that it hasn't won. It is called supercooling, and to understand it, you need to understand that water does not always freeze at 0 degrees Celsius. This surprises people because it seems to violate something very basic. 0 degrees is the freezing point of water. This is the definition. This is what's printed in textbooks and used in recipes and calibrated into thermometers. And in most ordinary situations, it is correct. But in very clean, very undisturbed conditions, particularly when water is cooled slowly and carefully, and when there are very few dust particles or rough surfaces to give ice crystals something to form around, water can drop below 0 degrees Celsius and remain liquid. It is below its freezing point, but it has not frozen. It is in a state called supercooling. You can hold supercooled water in your hand and watch it remain perfectly liquid. Then you can disturb it, shake it, tap the container, drop something into it, and watch it snap instantly into ice, crystallizing so fast that you can actually see the process happen. This is real. This is demonstrable. This is a genuine behavior of water. Now here is the connection to the Mpemba effect. When cold water is put into a freezer, it tends to supercool. It drops below 0 degrees and stays liquid for a while, sometimes a significant while, before the ice crystals finally nucleate and the freezing process begins in earnest. Hot water, it has been observed, tends to supercool less. It has been through a heating process that has driven off gases, altered the dissolved content, perhaps changed the microscopic character of the water, in ways that give ice crystals better footholds, and so hot water cooling in a freezer may reach the actual moment of freezing sooner because it is less likely to linger in that frustrating below zero but still liquid state. If this is correctable, if the crucial difference is not in how fast the temperature drops but in whether the water spends extra time in the supercooled state before it commits to becoming ice, then the Mpemba effect is not really about the rate of cooling at all. It is about what happens at the threshold. The cold water arrives at 0 degrees first, in terms of temperature, and then stalls. The hot water arrives later, in terms of temperature, but transitions to ice more quickly. And the one that transitions first wins. This is one of the most compelling single mechanisms proposed for the Mpemba effect, and several careful studies have pointed to differences in supercooling behavior as a significant factor. It has the virtue of making the apparent paradox feel slightly less paradoxical. You are not asking the longer journey to be faster, you are asking one traveler to be less hesitant at the final gate. But even this, even the most compelling single candidate, comes with its caveats and its unexplained cases, and we haven't yet opened all the doors. There are dissolved gases to consider, and something unexpected about the way water's molecular architecture may be storing and releasing energy, and a surprisingly mundane explanation involving frost on a freezer shelf. And there is, held in reserve for later, the most unsettling door of all, the one that asks whether the whole house might be built on ground that is less solid than we assumed. But that door can wait. It will still be there when we come to it. For now, settle a little deeper into wherever you are. The history has been told, from Aristotle's careful Meteorologica, to Bacon's Novum Organum, to Descartes' quiet corroboration, to the school kitchen in Tanzania, and the physicist who listened, and the paper that changed everything. The boy who refused to let it go now has his name on the effect, and the effect now has its proper place in the literature. And the mystery, the real, genuine, still open mystery, is only just getting properly started. So let us open the next door. We have been speaking for a little while now about the phenomenon itself, the bare, stubborn fact of it. That hot water under certain conditions can freeze before cold water, that this is not a myth or a trick or a misremembering, that Aristotle wrote it down, that Francis Bacon wrote it down, that René Descartes wrote it down, that a teenager in Tanzania noticed it in a school kitchen in 1963 and was laughed at, and that a physicist named Dennis Osborne listened anyway and ran the experiments and confirmed it and published the paper that gave the boy's name to the mystery forever. We have spoken about supercooling, that strange, suspended state in which water drops below 0 degrees Celsius without yet becoming ice, hovering in a kind of reluctant liquid limbo until something tips it over. And we have noted that previously heated water sometimes supercools less, crosses the threshold sooner, and transitions into ice while the cold water is still hanging back. A compelling mechanism, a real one, supported by careful observation, but not the only one, and not the final one, because there are other suspects, several of them, each with their own logic, their own evidence, their own particular elegance, and each with their own weaknesses, their own unexplained cases, their own failure modes. This is what the genuine scientific puzzle looks like up close, not a tidy hierarchy of explanations, not one breakthrough that dissolves all the others, but a room full of suspects, each with a plausible alibi and a plausible motive, none of them fully convicted by the evidence, and the detective, the scientific community, gathered over decades, still unable to reach a clean verdict. Let us meet them one by one. The first suspect is one you may have thought of already. It is, in some ways, the most intuitive of all of them, and it has a certain beauty in its simplicity. Hot water evaporates. You know this. You have watched it. You have set a pot of tea on a table and come back 20 minutes later to find it cooled and slightly lower in the cup. You have seen the steam rising from a hot bath. You have noticed that a puddle left by boiling water disappears faster than a puddle of cold water on a winter morning. The molecules at the surface of hot water are moving faster, far faster, than those in cold water, and faster-moving surface molecules are more likely to escape from the liquid entirely, to break free into the air as vapor. So here is the mechanism. When you put a container of hot water into a freezer, it begins losing not just heat, but mass. The water evaporates, and smaller amounts of water take less time to freeze because there is simply less of it to cool down, less of it to transition from liquid to solid. The hot water, in effect, has a head start, not because it cools faster in any rate-based sense, but because it has less to do. This is elegant, and it is, in a narrow set of circumstances, almost certainly part of what is happening. There is more, though. Evaporation is not only a matter of lost mass. Evaporation is itself a cooling process. When water molecules escape from the surface of a liquid, they carry energy away with them. Kinetic energy, thermal energy, the restlessness of heat. The liquid left behind is calmer, cooler. A wet cloth on a feverish forehead works partly on this principle. A swimming pool feels cold when you first climb out, as the water on your skin evaporates and pulls warmth away with it. Evaporation is an engine of cooling in its own right, and a container of hot water evaporating in a freezer is, in a small but real way, helping to cool itself. So we have two contributions from evaporation: less total mass to freeze, and active cooling through the evaporative process itself. Taken together, this is a reasonable explanation, a satisfying one even, and for many years it was the first explanation that people reached for, the comfortable, intuitive answer. But science, when it is working properly, does not stop at the comfortable answer. It does what Osborne did with Mpemba's question in the first place. It pushes further. It asks what happens if you remove the variable. What happens, scientists asked, if you run the experiment in a sealed container, one where evaporation cannot occur, where no water can escape, where the mass stays constant for both the hot and the cold sample? And the answer in several of those experiments was that the hot water still sometimes froze first. Not always, not consistently enough to satisfy everyone, but enough times in enough careful experiments that the result could not simply be dismissed. The effect did not vanish when evaporation was ruled out, which means evaporation may contribute. It may, in open containers under ordinary conditions, be part of what is happening, but it cannot be the whole story. There is something else, or several something else's, operating underneath. So evaporation is our first suspect, present at the scene, contributing to the outcome in some cases, but not sufficient to explain everything and not capable of standing alone as the full answer. The alibi holds in some circumstances and breaks down in others. We set it aside or dismissed, but not convicted either, and we turn to the next one. Convection. This one requires you to imagine water not as a still, uniform thing, but as something alive with motion. Because it is. When you heat water unevenly, or heat it from below, or let it begin cooling from the top, the water does not simply sit there and wait. It moves, it circulates. The warmer water, being slightly less dense, rises. The cooler water, slightly denser, sinks. Currents form. Slow, rolling, almost imperceptible currents that are nonetheless moving heat around the container the entire time. These are convection currents, and they are happening in any body of water that is not perfectly uniform in temperature. They happen in the oceans, they happen in your kettle before it boils, they happen in the atmosphere, driving weather patterns that span continents, and they happen in the container of hot water sitting in your freezer. Here is the proposed mechanism. Hot water develops strong convection currents as it begins to cool. The top layer of the water loses heat to the cold air in the freezer, cools, becomes denser, and sinks. Warmer water rises from below to replace it. This circulation keeps the water near the top relatively warm for a while, but it also means that the whole body of water is constantly being mixed, constantly having its heat redistributed and brought to the surface where it can radiate away. The water is, in a sense, turning itself inside out, continuously bringing its warmth to where it can be lost most efficiently. The phrase some researchers have used is the hot top. When hot water sits in a freezer, the top layer, through radiative and conductive losses to the surrounding cold air, becomes particularly active in shedding heat. The convection currents that develop in hot water may create a particularly efficient system for moving thermal energy toward the surface and out. Cold water, starting closer to zero, develops weaker convection currents. The temperature differential driving the circulation is smaller. The mixing is less vigorous. The heat does not move around as efficiently. In a subtle, mechanical sense, the cold water may be less good at getting rid of its own heat than the hot water is. This too is a real effect. Convection is genuine physics, not speculation. The currents are real. The mechanism is plausible. And in 2012, when the Royal Society of Chemistry held a public competition inviting the world to explain the Mpemba effect, a competition that drew over 22,000 entries from around the world, the winning entry, submitted by a researcher named Nikola Bregovic, emphasized both convection and supercooling as the strongest contributing mechanisms. 22,000 entries from students, from amateur scientists, from physicists, from engineers, from curious people who had stood in their kitchens and wondered, all of them brought in their various ways to bear on a question that had been waiting for an answer since before the Roman Empire. And the winner pointed to convection and supercooling, so convection is not a fringe idea. It is, according to the Royal Society of Chemistry's best assembled judgment in 2012, one of the leading candidates. It has the weight of institutional credibility behind it. It has the logic of real fluid dynamics. And yet it still cannot be declared the winner, because the experiments do not consistently support it as a universal explanation any more than evaporation does. There are conditions under which the Mpemba effect is observed that do not clearly show the signature of convection currents as the dominant factor. There are geometries of container, temperatures of starting water, and designs of freezer environment in which convection cannot plausibly be the answer. And there are experiments in which attempts to control for convection, to minimize it, to equalize it between the hot and cold samples, still sometimes show the hot water freezing first. Like evaporation, convection is probably real, probably present, probably contributing in some configurations, but it is not the single unified answer. It is a piece of a picture that will not quite resolve into clarity. You may notice a pattern forming here. Each mechanism arrives with excellent credentials, each has genuine physical logic, each is supported by some evidence, and each, when tested carefully, turns out to be insufficient on its own, present and contributing in some cases, absent or overwhelmed in others. This is not a failure of the science, it is what the science is honestly telling us. The Mpemba effect, whatever it is not a simple, single mechanism phenomenon. If it exists robustly, and we will come to the question of whether it does, it likely exists because of a combination of factors, not one clean cause. But we are not done with the suspects yet. Dissolved gases. Water, as you probably know in some vague way, is not pure. The water in your glass right now, even clean drinking water, contains dissolved gases. Oxygen, carbon dioxide, nitrogen, others. These gases dissolved into the water from the air, and they are simply there, invisible, mixed in at the molecular level. You would not know they were there just from looking. but they are. Here is the key property. Hot water holds less dissolved gas than cold water. This is a general principle of chemistry. Gases are typically less soluble in liquids at higher temperatures. When you heat water, you drive dissolved gases out of it. You have seen this happen. When you pour cold water into a saucepan and begin heating it, small bubbles appear on the sides and bottom of the pan well before the water comes anywhere near boiling. Those bubbles are dissolved gases coming out of solution, driven out by the rising temperature. They cling to the surface for a moment, then rise and escape. So hot water, water that has been heated and then placed in a freezer, starts with significantly less dissolved gas than cold water that was never heated. The proposed mechanism is that this difference in dissolved gas content changes the water's freezing behavior in meaningful ways. Lower dissolved gas content may alter the water's heat conductivity. It may change the way ice crystals nucleate and form. It may affect the structure of the freezing process in subtle ways that collectively allow the hot water to transition to ice more readily. Some researchers found this mechanism appealing because it operates at the molecular level, not a mechanical effect like evaporation or convection, but a change in the actual chemistry of the water, in the composition of the liquid being frozen. If dissolved gases are inhibiting or slowing the freezing process in cold water, then their relative absence in hot water could give hot water a real structural advantage. This is plausible, and it connects to a broader truth about water that is worth pausing on for a moment, gently. Water is not a simple thing. It behaves in ways that are genuinely unusual compared to most liquids. It expands when it freezes rather than contracting. It has an unusually high boiling point for a molecule of its size. It is, in a number of specific, measurable ways, an anomalous substance. So the idea that subtle variations in its dissolved gas content could meaningfully affect its freezing behavior is not inherently implausible, but the evidence for dissolved gases as the primary mechanism is, among all the candidates, probably the most mixed and contested. Some experiments designed to test this specific mechanism found effects consistent with dissolved gases playing a role. Others found no significant contribution. The relationship between dissolved gas content and freezing time has proven difficult to isolate cleanly from all the other variables: evaporation, convection, container geometry, freezer behavior, that are simultaneously in play. And so dissolved gases join the list, a real physical difference between hot and cold water, a plausible mechanism, some supporting evidence, and an inability, so far, to stand alone as the complete explanation. We are building a picture of a phenomenon that seems to have no single cause, or perhaps a phenomenon whose cause depends entirely on the specific conditions of each experiment, which is itself a kind of answer. Different experiments, different temperatures, different containers, different freezers, different initial conditions, different dominant mechanisms. In one case, evaporation carries most of the weight, in another, supercooling, in a third, convection, and always a residue of unexplained variance. But there is still another suspect. This one is newer than the others, proposed within the last decade, and it reaches down to a level of description that makes all the previous mechanisms feel almost macroscopic by comparison. Hydrogen bonding. To understand this one, you need to hold in your mind a small image of what water actually is at the molecular level. A molecule of water, H2O, is two hydrogen atoms bonded to one oxygen atom. You probably remember this from school. What you might remember less clearly is that water molecules don't just sit next to each other, isolated. They reach out to one another. The slightly positive charge of the hydrogen atoms in one molecule is attracted to the slightly negative charge of the oxygen atom in a neighboring molecule. This attraction forms what chemists call a hydrogen bond. Hydrogen bonds are not as strong as the covalent bonds holding each water molecule together internally. They are more like gentle pulls between neighbors, a kind of molecular sociability. But they are real. They are constantly forming and breaking and reforming as water molecules move around, and they give water much of its unusual character, its surface tension, its relatively high boiling point, its specific heat capacity, and many of the other properties that make it strange and useful and ubiquitous in the way that it is. Now, when water is heated, its molecules move faster and more energetically. And as they do, the hydrogen bonds between them are stretched. They don't break entirely, at least not at the temperatures we're discussing, but they are extended, pulled like elastic bands under tension. In 2017, a research team, Tao and Zheng and their collaborators, proposed a specific hypothesis that these stretched hydrogen bonds in warm water store energy within the covalent OH bonds of the water molecule itself. The idea is that when hydrogen bonds stretch, the internal bonds of the molecule relax slightly to compensate. They shorten, they store energy in a different form. And when hot water begins to cool, this stored energy is released as the hydrogen bonds relax and shorten, allowing the cooling process to happen differently than it does in cold water, where the bonds were never stretched in this way. The hypothesis is intricate. It requires thinking about energy storage and release at the level of individual molecular bonds, which is a long way from standing in a kitchen watching ice cubes. But the basic intuition is hot water has been, in some sense, wound up differently than cold water. Its internal molecular structure is not in the same configuration, and as it cools, it unwinds in a way that cold water, never wound up in the first place, does not. This is beautiful as a hypothesis. It has a kind of molecular poetry to it. The idea that heat leaves a memory inside the water, a structural imprint encoded in the geometry of stretched bonds, and that this memory influences what happens later when the water is asked to freeze. But it is, among the proposed mechanisms, also the most disputed. The 2017 hypothesis generated significant scientific discussion, some of it supportive and some of it sharply skeptical. Critics argued that the energy stored in stretched hydrogen bonds is too small, too distributed, too difficult to detect reliably, and too easily disrupted by other factors to account for a macroscopic effect as large as measurably faster freezing. The experiment required to definitively test this hypothesis at the molecular level is genuinely difficult, and the debate has not been conclusively resolved. So the hydrogen bonding hypothesis sits in an interesting position in the suspect lineup, the most molecularly sophisticated of the candidates, the most conceptually novel, the one that reaches deepest into the actual structure of water, and also the one with the most contested evidence and the least consensus support. It is the candidate the other candidates might find most interesting to argue with. We do not convict it, but we do not dismiss it either. We leave it in the room with the others unresolved, and then there is the last suspect, the one that is, in some ways, the most embarrassing, not because it is wrong, but because of how ordinary it is. Because after all this molecular architecture, all this convection and supercooling and hydrogen bonding and dissolved gases, one of the explanations that has genuinely contributed to observed Mpemba effect results in real-world experiments is this: frost on a freezer shelf. Bear with this for a moment. Or A. When you place a container of hot water in a domestic freezer, the bottom of that container is warm, warmer than the frost that typically coats the shelf, and a warm container melts the frost beneath it. Not completely, not into a puddle, but enough to deform it, to compress it, to change its texture. What this means is that the warm container ends up sitting in better thermal contact with the freezer shelf than a cold container does. The cold container, placed on unmelted frost, is insulated slightly from the shelf by that layer of frost, the way a sleeping bag insulates you from the cold ground. The hot container, having melted its frost layer, sits more directly on the cold metal, and better thermal contact with the cold shelf means faster heat transfer out of the water. This is not a profound molecular mechanism. It is not an ancient philosophical puzzle. It is frost on a shelf. And it matters. Several researchers and commentators have pointed to this explanation as a genuine contributor to observed results in domestic freezer experiments, the kind of casual experiments that most people run when they first hear about the Mpemba effect and want to try it at home, the kind that Erasto Mpemba might have been running in the school kitchen, not a sealed laboratory cryostat with precisely controlled variables, but an ordinary freezer with whatever happens to be in it. In a domestic setting, frost layer thermal contact may be responsible for a meaningful portion of the cases in which people observe hot water seeming to freeze faster. Not because of anything subtle about the physics of water, but because of the geometry of heat transfer and the mundane fact that frost is an insulator. There is something humbling about this. All those centuries of curious observation, Aristotle writing about antiperistasis, Bacon noting the behavior in Novum Organum, Descartes corroborating it, Mpemba refusing to let it go despite his teacher's mockery, Osborne running the experiments, 22,000 people entering a competition to explain it. And part of the answer might be, the hot container melted the frost it was sitting on. Science is often like this. The most thrilling mysteries sometimes have pieces that are small and ordinary and slightly anticlimactic, but this is not a reason to be disappointed. It is a reason to be careful. It is part of why the Mpemba effect has proven so difficult to nail down definitively in the laboratory, because in laboratory settings, frost layers are controlled for, containers are standardized, shelves are uniform. The mundane domestic explanation does not apply, and yet the effect, in some experiments, still sometimes appears, which means even taking away the frost, even sealing the container against evaporation, even controlling for convection, even equalizing dissolved gas content, there is still something happening, or at least there appears to be in some experiments, sometimes. And this right here is the most honest thing we can say about the Mpemba effect as it stands tonight. We have a collection of plausible mechanisms, each of which may be contributing in various conditions, none of which is sufficient on its own to explain every observation, and all of which together still do not add up to a clean, universally accepted, mechanistically complete account of why hot water sometimes freezes faster than cold. Evaporation, real, present, insufficient, alone. Convection, real, present, supported by some of the best institutional evidence, insufficient alone. Supercooling, arguably the strongest single candidate, present in several careful studies, still not universally conclusive. Dissolved gases, plausible, contested, unresolved. Hydrogen bonding, molecularly sophisticated, disputed, debated. Frost layer thermal contact, mundane, real in domestic conditions, irrelevant in careful laboratory settings. 6 suspects, none convicted, the case still open. And what is remarkable about this, Kim, what gives the whole situation its particular texture as a scientific mystery, is that these suspects are not wildly exotic. We are not talking about dark matter or the quantum behavior of black holes or some phenomenon that can only be observed inside a particle accelerator at energies that don't exist in nature. We are talking about water in a freezer. Something that happens, or appears to happen, in kitchens around the world. Something you could try tonight if you wanted to, with a glass of tap water and whatever freezer is available to you. The accessibility of the phenomenon is part of what makes its persistence as a mystery so striking. Most of the great unsolved questions in physics require instruments of staggering complexity to even observe the phenomenon in question. The Mpemba effect can be observed with no equipment at all beyond what exists in the ordinary domestic environment, and it is still not understood. That combination, trivial to demonstrate, impossible to fully explain, is rare in science, and it gives the Mpemba effect a peculiar status, a kind of approachable inscrutability. There is a thought worth holding here as you settle wherever you are as the night continues to do its quiet work. Science does not know everything. This is not a failure of science. It is simply the current boundary. And the boundary is not in this case at the outer edge of the universe or the inner heart of a particle. It is at the boundary of a glass of water. A glass of water that under certain conditions not fully understood, not consistently reproducible, not yet attributed to any single agreed-upon mechanism, can freeze faster when it starts out hot than when it starts out cold.
Aristotle noticed this, Bacon noticed it, Descartes noticed it, a schoolboy in Tanzania noticed it, was laughed at and persisted. A physicist listened and ran the experiments and wrote the paper. 22,000 people tried to explain it. Nikola Bregovich won the Royal Society of Chemistry competition, pointing to convection and supercooling, and even that is not the end of the conversation.
Because there is still the 2017 hydrogen bonding hypothesis sitting in the literature, disputed but not refuted, and there are still the sealed container experiments that evaporation cannot explain, and there are still the cases that supercooling, on its own, doesn't quite account for. The suspects are all in the room, and the verdict has not come. Somewhere along the way, if you have been half listening, which is exactly the right way to be listening to this, at this hour, in this quiet, you may have developed a sense of the shape of the mystery. Not the answer, but the shape. A phenomenon observed across 23 centuries. Proposed mechanisms that are each real and each insufficient. A question that invites experimental work but resists decisive experimental resolution. A puzzle not at the frontier of unreachable physics but in the most ordinary substance on Earth. And the mechanisms we have been through, evaporation, convection, supercooling, dissolved gases, hydrogen bonding, frost on a shelf, are not the last word. Because the scientific conversation about the Mpemba effect has not stopped. It has, in recent years, taken some genuinely unexpected turns. Turns that lead away from the kitchen, away from the freezer, into territory that when you first hear it described, sounds almost like it couldn't possibly be about the same phenomenon. But it is. Or it might be, and this is where the story is going next. For now, though, the suspects have been introduced. You have met each of them. You know their strengths and their weaknesses. You know that none of them, on their own, has been enough. And you know that the case is still open, that scientists who study this question for a living have not yet reached the clean verdict that the phenomenon seems to be waiting for. That is where we are. 6 mechanisms, none decisive, a mystery that has been waiting for its resolution since before Julius Caesar was born and is still waiting tonight. Rest with that a moment if you like. There is no hurry here. The water is in the freezer. The night is doing its slow, patient work, and the answer, if it exists in the form we are looking for, has not arrived yet, which means we get to keep going a little further. So, where were we? 6 suspects, none convicted, a mystery older than algebra, younger than the last time anyone bothered to solve it, and a promise, made quietly, somewhere back in the early part of this journey, that the story was not finished, that the conversation about the Mpemba effect had taken unexpected turns, that the next chapter of this puzzle led somewhere surprising. Let us go there now. The year is 2012, not 1963, not 350 BCE, not 1969, 2012, and the Royal Society of Chemistry, one of the oldest and most respected scientific institutions in the world, based in London, with a history stretching back to 1841, decided to do something rather unusual. They decided to hold a competition. The question they put to the world was this one: what causes the Mpemba effect? Explain it, if you can. Now, the Royal Society of Chemistry is not in the habit of hosting public competitions for questions that are already answered. You do not invite 22,000 people to explain something that is sitting in a textbook with a clean, verified, universally accepted solution. The competition was itself a kind of institutional acknowledgement, a quiet admission, dressed up in the language of public engagement, that here was a genuine open question, that the four mechanisms the textbooks listed, evaporation, convection, supercooling, dissolved gases, were candidates, not conclusions. That nobody, really, had gotten there yet. 22,000 entries from all over the world, from students and professors and amateur enthusiasts and retired engineers, sitting at kitchen tables at midnight, each of them with an idea, a theory, a framework, a hunch. 22,000 people who had thought about ice and water and heat and decided they had something worth saying. That number should settle into you for a moment. 22,000. If you lined those entries end to end, the pages, the diagrams, the hand-drawn graphs and emailed submissions, you would have something like the accumulated intellectual attention of a small city, all pointed at one glass of water and one freezer and one unanswered why. The competition had a winner. His name was Nikola Bregovich, and his winning entry leaned, as you might already have guessed from our long walk through the suspects, on two of the mechanisms we have already spent time with: convection and supercooling. The argument at its heart went something like this. Hot water, when placed in a freezer, develops those convection currents. The warm water rising, the cooler water sinking, the mixing and the circulation that creates a more efficient transfer of heat away from the container. And separately, previously heated water tends to supercool less than water that was never heated. It reaches the freezing point and begins forming ice closer to 0 degrees Celsius, while colder water might sink several degrees below zero before its crystals start to form. So the hot water, paradoxically, reaches the moment of crystallization sooner. Two mechanisms working together, not just one, a combined effect that was stronger than either process alone. It is a compelling argument. It is the kind of argument that feels like it could be the answer, and it won the most significant public competition ever held on this specific question. But here is the thing, winning a competition, even one run by the Royal Society of Chemistry, even against 22,000 other entries, is not the same as solving a problem. The winning entry is the best argument submitted to that competition on that day, judged by those particular experts using those particular criteria. It is not a peer-reviewed experimental proof. It is not the kind of evidence that closes a question in physics. It is a strong, well-reasoned proposal, which is meaningful, and also, genuinely, not enough to end the debate. Because the debate did not end, and part of the reason it did not end is something we have been dancing around for the whole of this journey, something that sounds almost too simple to be the crux of a 2,300-year-old scientific controversy, but which turns out, on examination, to be absolutely central. Nobody agrees on what the words mean. I want to stay with that for a moment because it is easy to pass over it and harder to really absorb. The question the Mpemba effect asks is, does hot water freeze faster than cold water? But to answer that question scientifically, to run an experiment that gives a clear yes or no, you need to know what you mean by freeze and what you mean by faster. And it turns out that both of those words in this context are genuinely ambiguous, not vague in an everyday sense, ambiguous in a technical, experimentally consequential sense. What does it mean for water to freeze? You might say it means it has turned into ice. But the transition from liquid to solid is not a single moment. It is a process. So does freezing happen when the first ice crystal appears, when the surface of the water first shows ice, when the entire volume of the container has become solid, when the temperature in the center of the container reaches 0 degrees Celsius, when some thermometer in some location in the freezer registers a particular reading. Each of those definitions is reasonable. Each of them is also different from the others. And depending on which definition you choose, the same experiment can give you a different answer. The same two containers of water, one initially hot, one initially cold, can appear to show the effect or not show the effect, depending purely on what your thermometer is measuring and when you decide to stop the clock. This is not a trivial technical quibble. This is the definitional heart of the problem. If there is no consensus on what freezing means in this context, then different laboratories running different experiments with different methodologies will get different results. And then those different results will be compared as though they are measuring the same thing. And the literature will accumulate contradictory findings, not because the physics is different in different laboratories, but because the question is not quite the same in each one. There is something almost philosophically vertiginous about that. A phenomenon named after a person, debated by thousands of people, written about for 2,300 years. And one of the central obstacles to resolving it is that the community has never quite agreed on what the phenomenon is, on what the words in the question mean, on how to recognize the thing you are looking for when you are looking for it. And this definitional ambiguity feeds directly into what came next, into the most striking single moment in the modern history of the Mpemba effect, into a paper that, when it was published in 2016, drew more attention and more discomfort than perhaps any other piece of writing on this subject since Mpemba and Osborne's coup in 1969. The paper was written by Henry Burridge and Paul Linden. It appeared in Scientific Reports, and its title did not leave much room for ambiguity about what the authors were arguing. The title was Questioning the Mpemba Effect. Hot water does not cool more quickly than cold. Hot water does not cool more quickly than cold. Not. Hot water sometimes freezes faster, and here is a more refined explanation for why. Not. The mechanisms are more complicated than we thought. Hot water does not cool more quickly than cold. Full stop. Burridge and Linden looked at the existing experimental literature and found it inconsistent to a degree that was, in their assessment, fatal. Not just results vary, but results vary so wildly under conditions that should, in principle, be comparable, that the variation itself is the story. The effect, they argued, had never been demonstrated in a robust, reproducible, controlled way that met the standards we would normally demand before accepting that a phenomenon is real. They went further. They argued that part of the problem was exactly that definitional issue we just talked about, that because there is no standard definition of what freezing faster means, different experiments were essentially measuring different things and calling them all by the same name, and that once you defined the question rigorously, once you pinned down exactly what frozen means and exactly how you were going to measure faster, the effect largely disappeared, all became so small and so inconsistent that it could not be called a robust physical phenomenon. This is a significant claim, not a fringe position from an unknown journal. Scientific Reports is a peer-reviewed journal associated with the Nature Publishing Group. Burridge and Linden are researchers at the University of Cambridge. This was not someone writing on a blog or posting a YouTube comment. This was serious institutional science making a serious institutional argument that the Mpemba effect, as it is conventionally described, as the counterintuitive but real and explainable observation that hot water freezes faster, may simply not be a real robust effect at all. Let that settle. You have just spent many hours, or perhaps a night, perhaps two, walking through the history of this question. You have met Aristotle and Bacon and Descartes and Mpemba and Osborne and the 22,000 people who submitted entries to the Royal Society of Chemistry. You have learned about evaporation and convection and supercooling and dissolved gases and hydrogen bonds and frost on a freezer shelf. And now in 2016, two Cambridge researchers published a paper saying, "We are not convinced it happens. This is not quite the same as saying Mpemba was lying. It is not the same as saying Osborne did not observe what he observed. What Burridge and Linden were questioning was whether the effect, as observed under particular conditions by particular experimenters, generalizes into a broad, reliable, reproducible phenomenon that warrants a single name and a single explanation." Their argument was that it might not, that what we call the Mpemba effect might be a collection of loosely related observations that can each be explained by specific local conditions, a particular container, a particular freezer, a particular initial temperature, a particular definition of frozen, rather than a single, unified phenomenon with a single physical cause. And that argument is still being debated. The 2016 paper did not close the discussion. It opened a new chapter of it, because there were researchers who found its methodology and conclusions persuasive, and there were researchers who did not, who believed their own experimental data showed a real effect, who believed that the inconsistency in the literature was not evidence that the effect was illusory, but evidence that the effect was highly sensitive to conditions, which is different. A sensitive phenomenon is still a phenomenon. It is just a harder one to study. And so the conversation continued, as conversations about genuinely hard things tend to do. There is a quietness to that fact that I find almost beautiful. Not beautiful in a tidy, solved way, beautiful in the way that an open horizon is beautiful, or the way the night sky is beautiful, not because you can see everything, but because you cannot. 22,000 people had ideas about this in 2012. Two Cambridge researchers published a challenge to the whole foundation in 2016. And the question, as of the moment you are listening to this, remains open. The most ordinary thing, a glass of water in a freezer, is still keeping its secret. But the story does not quite stop there either, because in the years since 2016, something has happened that was not anticipated by the original debate. Something that has widened the Mpemba effect from a question about water and ice into something more abstract, and in its own way, more interesting. Physicists have found the Mpemba effect in things that are not water. Let me say that again, slowly, because it is a genuinely strange thing to say. The Mpemba effect, the phenomenon named after a Tanzanian schoolboy who watched his ice cream mix freeze, has been observed in systems that have nothing to do with ice cream, nothing to do with freezers, nothing to do with liquid water at all. The systems in question include granular gases, which is not a phrase that comes up at bedtime very often, so let me take a moment with it. A granular gas is not a gas in the ordinary sense, not oxygen or nitrogen or the air in your room. It is a system of many tiny particles, grains of sand, tiny beads, small spheres, moving and colliding with each other in a way that, mathematically, resembles the behavior of a gas. Physicists use granular gases to study the abstract principles of how systems with many interacting parts exchange energy and change state. And in granular gases, in computer simulations and in theoretical models, researchers have found a Mpemba-like effect. A situation in which a hotter system, meaning a higher energy state, using the physicist's definition of temperature as the average energy of the particles, cools down to a given state faster than a cooler system starting from the same conditions. Hotter goes first, which is, in mathematical structure, exactly the Mpemba effect. And then there are magnetic systems, systems of tiny magnets, or rather, of mathematical objects that behave like tiny magnets, that when disturbed away from their low energy state can relax back toward that state faster if they start from a higher energy configuration. Again, hotter in the abstract sense can reach a final state faster than cooler. These findings, which emerged through theoretical and computational work in the 2020s, suggest something that changes the nature of the question considerably. They suggest that the Mpemba effect might not be a specific quirk of water. It might be a more general mathematical phenomenon, a property of certain kinds of systems with certain kinds of energy landscapes when they are cooling toward equilibrium. It might be that water just happens to be one of the systems that can exhibit this behavior, alongside granular gases and magnetic systems, and possibly others we have not yet found. Physicists call this kind of thing a relaxation phenomenon. The idea is about how a system relaxes from a disturbed state back toward its equilibrium, its natural, lowest energy resting place. Most of the time, you would expect that a system farther from equilibrium would take longer to get there, but in certain systems with certain structures, a state that is farther away can have a kind of shortcut available to it, a pathway through the energy landscape that a state closer to equilibrium does not have access to, because being closer to equilibrium means being committed to a particular approach that is not the fastest one. It is a bit like two people trying to get to the same destination by walking through a landscape of hills and valleys. One person starts close to the destination but is standing in a valley that requires climbing a hill before descending. The other person starts farther away but is on a ridge that leads directly down. The farther person arrives first, not because of anything strange or magical, but because the shape of the landscape and the structure of the available paths favored them. And that is what the theoretical work on Mpemba-like effects in non-water systems is suggesting, that the Mpemba effect might be, at its deepest level, a story about the shape of energy landscapes, about which systems have shortcuts available to them and which do not, about how the structure of the internal pathways available to a system determines which starting point reaches the destination first. Whether this abstract, generalized understanding connects back to the specific, kitchen-level literal question, does hot water in your freezer freeze before cold water, is itself still a genuinely open question. The theoretical work in granular gases and magnetic systems is exciting, and it is real, and it may point toward a deeper understanding of why the Mpemba effect in water exists. But it is not yet a settled connection. It is not yet the final link in the chain that goes from Erasto Mpemba's ice cream mix in 1963 to a clean, unified, fully accepted explanation. The chain is longer than it looks, and that is all right. Because here is where we have arrived. The Mpemba effect has been observed in one form or another since the 4th century before the Common Era. Aristotle wrote it down, Francis Bacon wrote it down, René Descartes wrote it down. For roughly 2,300 years, the observation sat in the literature of natural philosophy and later of natural science, noticed, recorded, and then quietly set aside. Then, a teenage boy in Tanzania around 1963 noticed it again in a school kitchen, was ridiculed, asked a visiting physicist anyway. And that physicist, Dennis G. Osborne, rather than dismissing the question, went and ran experiments and published a paper and gave the phenomenon a name. And in the years since, it has drawn 22,000 competition entries from the public, a challenge from Cambridge researchers who argued it might not be a real effect at all, a winning hypothesis about convection and supercooling from Nikola Bregovich, a 2017 molecular-level proposal from Tao and Zheng about hydrogen bonds, and a strange new chapter in which the effect seems to appear, in some abstract mathematical sense, in magnets and in grains of sand.
And still no single accepted explanation, still no clean verdict, still no entry in the textbook that says, here is why, here is the mechanism, here is the proof, here is the answer.
This is, if you let it be, one of the most quietly remarkable things about the world we live in. Not remarkable in a frightening way, not a reason to distrust science or to feel that the project of understanding things is hopeless. Quite the opposite. It is remarkable because it means the project is alive, that the questions have not all been answered, that the straightforward and the everyday still contain surprises, You have almost certainly a freezer somewhere nearby, maybe in the kitchen, maybe down the hall, and in that freezer at this moment there may be a tray of ice, or a bag of vegetables, or a container of something that once was liquid and is now solid. And the process by which that happened, the physics of the water molecules settling into their crystalline lattice, slowing down, locking into place, is something that human beings have understood in outline for well over a century. And yet, in the specific particular case of whether the same water starting from a hotter temperature would have done that faster than if it had started cold, we do not fully know. We have hypotheses, we have candidate mechanisms, we have experiments that show yes and experiments that show no, and a definitional problem that makes it hard to be sure whether the yes and the no are even measuring the same thing. That is the position we are in tonight, right now, with all the centuries of accumulated scientific understanding behind us, with quantum mechanics and molecular dynamics and computational physics and the full weight of modern experimental technique at our disposal. We are in the position of not quite knowing, and I think there is something genuinely comforting in that, not because ignorance is comfortable, it is not always, but because an unsolved question means the world is still wider than our models of it, means that the ordinary things, water, cold, ice, are still capable of surprising us, still capable of being stranger than they look. Erasto Mpemba was laughed at for noticing something strange about an ordinary thing. And it took a physicist willing to take the question seriously, and a paper, and decades of work by many researchers, and a competition with 22,000 entries, and a challenge paper arguing it might not be real, and theoretical work in physics suggesting it might be a manifestation of something deep about the nature of systems in general, all of that, just to get to, we still do not entirely know. That is a long way to travel to arrive at an open question, but it is not the wrong destination, because the open question, when you sit with it, is not emptiness. It is not a gap where knowledge should be. It is the live, breathing edge of what is known, the place where the world is still being worked out, and those places are rarer than they used to be. As science has advanced, the comfortable mysteries have been one by one replaced by answers. The motion of planets, the structure of the atom, the composition of stars, the age of the universe, the mechanism of heredity. One by one, the great mysteries have been opened up and found to contain working explanations. The Mpemba effect is one of the ones that has not yet. And because it has not yet, it sits in an unusual place, somewhere between the kitchen and the frontier, between the completely ordinary and the genuinely unexplained, between what you can do with 2 glasses of water and a freezer and what the world's physicists, with all their instruments and all their mathematics, have not quite been able to pin down. There is a word for that place, I think. Several words, depending on who you are and what brings you comfort. Wonder, mystery, an open question, a place where the world is still teaching us something. Whatever word fits you, this is that place. And it lives in your freezer. I want to go back just for a moment to where this started. We began tonight, however long ago that feels now, with whatever lamp is still on, with the blanket you have arranged around yourself in the particular way you arrange things at this hour. We began with a boy, a secondary school student in Tanzania around 1963. His name was Erasto Mpemba, and he was making ice cream. He put the hot mixture in the freezer. He watched, he noticed, and the thing that gets me quietly every time I think about this story is not the observation itself. The observation is interesting, yes, but what gets me is the persistence. The fact that he was laughed at by his teacher, by his classmates, and he did not let the laughter be the last word. He waited. And when a physicist named Dennis Osborne visited, Mpemba asked his question. Not defensively. Not with the anger that might have been entirely warranted after years of mockery. Just the question. Directly, have you seen this? Does this make sense? What is happening? And Osborne, who could have done what many people would have done, which is to smile and offer a polite but deflecting answer and move on to something less embarrassing. Osborne went and ran experiments and found that Mpemba was right, that the observation was real, that it was worth writing about, that it was worth a paper in Physics Education published in 1969 with both their names on it, asking the simplest and deepest possible question in its title. Cool? A question mark, not an answer, a question mark. That paper, with its one-word title and its upward inflection, is now cited in physics literature around the world. The phenomenon it described is called the Mpemba effect. The boy who was laughed at has his name on something that Aristotle, Francis Bacon, and René Descartes all observed and none of them solved. His name is in a tradition that stretches back through the entirety of recorded European natural philosophy, and his name is the one that stuck, because he was the one who insisted on the question. That is a beautiful thing, a slow, quiet, unexpectedly beautiful thing, tucked inside what looked from the outside like a straightforward science question. The effect was noticed by Aristotle in his Meteorologica, written in the 4th century before the Common Era. In a text that has survived through ancient Greek, through medieval Arabic, through Latin translation, through the centuries of copying and marginal annotation and careful preservation that carried it to where we can still read it today. And in that text, Aristotle writes, with the same matter-of-fact directness with which he recorded everything, as though the world were obligated to yield its secrets to the sufficiently attentive eye, that water previously heated freezes more quickly, and that if you want cold water fast, you should stand it in the sun first. He called the principle antiperistasis, his own theoretical explanation for what was happening, a principle of heat and cold interacting in a particular way. The explanation by modern standards did not survive. The observation did. That is the gap. 2,300 years of gap. From Aristotle to Mpemba. From the ancient Mediterranean to a secondary school in Tanzania. And through all that time, through Bacon and Descartes and the scientific revolution and the development of thermodynamics and the invention of the refrigerator and the emergence of molecular chemistry and quantum physics and everything else, through all of that, the observation kept being made and the explanation kept not arriving. And tonight, on this side of all those centuries, in your room, in your corner of the night, the situation is not entirely different. The observation is still being made, the explanation is still being debated. The 2016 paper by Burridge and Linden is still in the literature, and the response to it is still being written, and the theoretical work on granular gases and magnetic systems is still being developed. And the question that Aristotle, Bacon, Descartes, and Erasto Mpemba all put into words is still open. That is the honest position. And the honest position on this question is the interesting one. Not despite the unresolvedness, because of it. Because a mystery that has been held open across 2,300 years of human thought is not a failure of human thought. It is a testament to the difficulty of the question, to the subtlety of the thing being asked, to the fact that ordinary water in an ordinary freezer is doing something that has not yet fully yielded to the tools we have developed to understand it. And you live in a world where that is still true, where the kitchen contains unsolved physics, where the glass of water on your bedside table, if you have one, and I hope you do, because staying hydrated matters, and also because it is a very convenient thing to think about right now, is doing things at the molecular level that remain in their full detail, a story still being written. That is not a reason for anxiety, it is a reason for something much quieter and much more sustaining. The world still contains more than we know. The boundary between the known and the unknown runs right through the most familiar things: water, cold, ice, a kitchen freezer. You do not have to go to the edge of the universe to find the frontier. You can find it in a glass of ice water. You can find it in the same question a teenage boy asked in Tanzania, and the same question Aristotle posed in a lecture hall in ancient Athens, and the same question thousands of people answered in entries submitted to the Royal Society of Chemistry in 2012. The question is still there. And there is something almost companionable about that at this hour. The mystery is not going anywhere. The scientists are still working on it. The experiments are still being designed and run and analyzed. Somewhere, right now, in some laboratory, or in someone's kitchen, because that is the lovely thing about this question. It is accessible to anyone with a freezer and 2 glasses and a thermometer and enough patience. Somewhere, someone is watching water freeze and trying to see what it does. And you are watching too in your own way, not watching water, watching a night go by, listening to a question that has been asked across 2,300 years and across more languages and more centuries and more quiet kitchen observations than we can count. You are a part of that long human tradition of noticing things, of paying attention to what is in front of you, of refusing to be entirely satisfied with the obvious explanation. Mpemba refused to be satisfied. He noticed something and he held on to the question, even when it was not welcomed. And eventually the question found its way into the literature and into the world, and now you know his name. That is how this works sometimes, slowly, with patience, with persistence, with a willingness to sit with something that does not resolve quickly or neatly or in the way you expected, which might, at this particular hour of the night, sound not entirely unlike something else you know. The best sleep does not arrive on command. It arrives when you stop reaching for it, when you settle, when you let the night be what it is, wide and quiet and patient and full of questions that will still be there tomorrow. The water is still in the freezer. Hot or cold, it will do what it does. And you do not have to know why to trust the process. Let the question rest where it is. Aristotle did not solve it. Bacon did not solve it. Descartes did not solve it. The 22,000 entries did not solve it. Burridge and Linden asked if it was even real. The theorists found it in magnets and sand. And still, the water keeps its secret. The night keeps its secret. And some things, it turns out, are comfortable to live beside without fully knowing. Wherever you are tonight, whatever lamp is still glowing, whatever window is letting in the small sounds of the dark, whatever corner of the world holds you at this particular moment, I hope this slow journey through one long mystery has given you something to rest in. Not an answer, something better than an answer, a question that has been kept company for more than 2,000 years. A question with your name on it in a way, because you are made of the same water that keeps its secrets, and you are a part of the same long story of noticing things and wondering why. You are right now approximately 60% water. The cells in your body are doing extraordinary things with that water, moving it, using it, keeping you alive in the dark without any effort on your part, without you needing to understand the mechanism. The water does what it does, your body does what it does. And somewhere in there, at the molecular level, in the behavior of hydrogen bonds and dissolved gases and the subtle architecture of your particular chemistry, there are probably things that science has not yet fully explained. That is not frightening. It is the normal condition of being a living, complex, incompletely understood thing in an incompletely understood world. And that too is all right. The Mpemba effect is still open, the mystery is still alive, the water is still in the freezer, and you who stayed with this question from its beginning through Aristotle and through Tanzania and through a paper called Cool and through 22,000 people's best attempts at an answer, you can let it go now. Let the question sit where it has been sitting for 2,300 years, patient and untroubled, waiting for the right moment. There is no hurry, there never was. If this slow journey through an unsolved mystery gave you something to carry into sleep, a little wonder, a little company, the quiet comfort of knowing that the world still keeps secrets even in the most ordinary places, then I am glad. Genuinely glad. And if you would like to say where in the world you are listening from tonight, and what time it is in your corner of the dark, I would love to know. Leave it in a comment when you wake. That small detail to your city, your time zone, the particular quality of your night, is the kind of thing that makes this feel less like a channel and more like a conversation, which is what I hope it is. If you enjoyed this slow drifting journey, a like and a subscribe help more than you might think. Small creators like me rely on your support to keep these nights going. And if you are already here, already subscribed, already part of this quiet traveling community, thank you, genuinely. You are the reason the curious voyager keeps sailing. The question will still be there when you wake, the water will still be in the freezer. And somewhere a scientist is watching it, wondering. Sleep well, fellow voyager. The next journey keeps until you wake.